Now let's start the 12th lecture. In the last lecture, we talked about what neural networks are. Today, we will talk about how to learn the parameters of neural networks in specific way. We will use a specific method called the backpropagation method. I want to explain this in detail. Uh, let's talk about what neural networks were like. When an input is given, we call it Z0. We multiply Z0 by weight, add bias, and put into activation function to get the next output Z1. We multiply, so we multiply Z1 by weight, add bias, and put it into activation function to get the next output. We repeat this process. We repeat this several times, and what comes out is the output of neural networks. This set of input and output repetition is called a layer. First, for our later discussion, let's call the thing before putting into the activation function, which is multiplying by weight and adding bias as u. In other words, for example, let the input be x, and we call it z to z, so well, z0. We multiply this by weight and add bias to get u, uh, and the output z to z1 that we mentioned before because becomes fu1. If we define u in this way, to decide parameters, we use stochastic gradient descent. For this, we need two gradients, which means partial derivatives. Since parameters are w and v, we need to calculate partial derivatives of the loss function L with respect W and the partial derivative is with respect to B. But how do we calculate them? This becomes a problem. So what we want to do with propagation is to calculate these partial derivatives. This is our motivation. Starting with general theory would be complicated, so let's try with a single layer neural network first. Let's also make the dimension of each layer a 1. Let's say we have training data x and y pairs. The predicted value is y hat. And since each layer has one dimension, we can write it as a scalar. For example, let's choose mean squared error as the loss function. In other words, let's make it half of the square of the difference between the predict value and the actual value. Then, since the predicted value is y hat, L become 1 half times y hat minus y squared. The partial derivative in this case are simple. Alright. And the partial derivative with respect to weight W is since the derivative of something square, so something square is 2 times something. So it first becomes like this. So this part. Next, in the partial derivative part with respect to f w1x plus b1, f prime comes out. Finally, since w1 is multiplied by x, x comes out. For the partial derivative with respect to b, we want the squared part is similarly differentiated. So this passing. The derivative with respect to f comes out. And finally, since nothing is multiplied to the bias, 1 comes out. We can calculate it this way, but for later purposes, we can see that this partial derivative is a partial derivative of L with respect to u1 multiplied by the partial derivative with respect to u2 w1. Since u1 is a function of w to the power w1, when we take the partial derivative with respect to w1, we multiply the partial derivative of L with respect to u1 by the partial derivative u1 with respect to w1. The partial derivative of L with respect to u1 part, so this part, becomes f w1 x plus b1 minus 1. Also, yes. So L is 1/2 times fu1 minus y square. The partial derivative of L with respect to u1 is f w1 x plus b1 minus 1 times f prime u1. So this corresponds to here. When we differentiate the partial derivative of u to u1 with respect to w1, we get x. When we differentiate the partial derivative of u1 with respect to b1, we get 1. So the partial derivative becomes like this. This is just rewriting that we did before this one, so we don't see the benefit yet. But next, let's try with 3 layers. Let's say we have 3 layers and each dimension is y1. And the calculation of values inside the neural networks was done like this. First, in the first layer, we multiply the input by W1 and add B1 to get U1. We put u1 into the activation function f to calculate the first layer output z1. So z1 equals fu1. For the second layer, we use this z1 that came out multiplied by weight W2 and add bias P2 to calculate U2. We put this U2 into F to get Z2. Uh, this is output of the second layer. Using this Z2, we multiply weight W3 and add the bias B3 to get U2 the U3. We put this into activation function f and the y hat that comes out becomes the output of the entire neural network. In other words, it becomes a predicted value. So when we choose mean squared error as a loss function, just like this, uh, the loss function becomes a function determined by W1 to W3 and B1 to B3. It is defined as one half of square of difference between the predicted value and the actual value. Looking back at the previous page, so what we need to know first is the partial derivative of L with respect to u. If we calculate the partial derivative with respect to u, the later calculations becomes simple. Well, since since L can be here. Since L can be written with the previous y hat as fu3, L can be written as one half times fu3 minus y squared. The partial derivative of L with respect to u3, just like before, similar to the single layer neural network, becomes something squared. So the derivative of comes out, and the partial derivative f u to the u3 with respect to u3 becomes f prime u3. To calculate the partial derivative with respect to W3, this is the same as multiplying the partial derivative with respect to u3 by the partial derivative u3 with respect to W3. Since the partial derivative of L with respect to u3 can be like this, we need to calculate the partial derivative u3 with respect to w3. Since u3 can be yes, u3 can be written as w3. Uh, so w3 times z2 plus b3. When we take the partial derivative with respect to W3, Z to the Z2, this part, comes out. So the partial derivative with respect to W3 becomes like this. Next, since we could calculate the partial derivative with respect to W3, the question becomes what happened to the partial derivative with respect to W2? We want to do the partial derivative with respect to W2 directly, but doing it directly is difficult. So just like this, we consider the partial derivative is respect to U2. The partial derivative of L with respect to W2 can be written as the partial derivative L with respect to U2 times the partial derivative of U2 with respect to W2. Uh, the partial derivative of L with respect to U2 can be written as the partial derivative L with respect to U3 times the partial derivative of U3 with respect to U2. If we put U3 in between, we calculate the partial derivative, uh, complicated. So dl du3 before we have this one. We need to calculate the du3 du2, but u3 U3 is W3 Z2 plus B3. So U3 is equal to W3 FU2 plus B3. So DU3 DU2 is W3 F prime U2. Okay, on the other hand, so U2, so where is, here. U2 is W2 times Z1 plus B2. So, the partial derivative of U2 with respect to W2 is Z1. This way, we could calculate the partial derivative with respect to W2. Next, what happens to the partial derivative with respect to W1? Just like before, if we put U1 between, it can be written as dl dw1 equals dl du1 times du1 dw1. The question is what the partial derivative what dl du1 is, but if we put u2 in between, so dl du1 equals dl du2 times du2 du1. We calculate the dl du2 here uh, before, so we know what's inside here. What is du2 du1? Using the same method as before, U2 is W2 Z1 plus B2. And Z1 is f of u1. So u2 equals w2 f u1 plus b2. So du2 du1 is w2 f prime u1. Okay, and finally, u1 is w1 x plus b1. So du1 dw1 is x. Therefore, the partial derivative of L with respect to w1 becomes like this. From the calculation we have done so far, I think you can see the calculating the partial derivative of L with respect to u something first to make the later calculation simple. You can see that the partial derivative of L with respect to u is important. Let's call the previous partial derivative L with respect to u as delta. Then delta 3 is y hat minus y f prime u3, and so delta 2, which corresponds to the partial derivative of L with respect to u2, so this one, which is so delta 3 times w3 f prime u2. So we obtain this one. So the same story, delta 1 is dl du1, so this one. And dl du1 equals dl du2 w2 f prime u1. dl du2 is delta 2, so we obtain this equation. So if we calculate in reverse once delta 3 is determined, delta 2 is also determined, and once delta 2 is determined, delta 1 is determined in chain-like form. By using this delta to the power the delta 3 to delta 1, we can also calculate the partial derivative with respect to weight w. Specifically, the partial derivative, so dl dw3 becomes delta 3 times delta 2. dl dw2 is delta 2 times z1. dl dw1 is delta 1 times x. So far, we have only talked about weights, but the partial derivative with respect to bias are similar. If we change the z part to 1, so 1, it becomes a partial derivative with respect to bias. So once this delta can be calculated, both partial derivative with respect to weights and partial derivative with respect to bias can be calculated. And this delta 3 delta 3 is based on the initial y hat minus y, which means it's a value determined by the error y hat minus y. Furthermore, delta 3 is determined, then delta 2 is determined, then delta 1 and so on, with the subscripts getting smaller. In feed-forward neural networks, Z has determined in order from smallest. Z, Z1 was determined, then Z2 was determined, Z2, Z3 was determined, and so on. So compared to that, they are determined in reverse order. So since the value determined by error and are determined in reverse order for delta, it is called the backpropagation method. Okay. Let's take a break. Okay, let's restart. Let's see how the numbers are determined through specific calculations. Actually, we rarely calculate by hand in rare situations. We let the compute do it. But let's try calculating to see how the numbers are determined. For simplicity, let's use a sigmoid function as the activation function. Well, and make each layer one dimension. The value inside the neural networks determine like this for training data. Let's use mean square error as the loss function. Actually, since we are putting with sigmoid function at the end, it would be better to use log likelihood, but the calculation procedure is easier with this, so let's try this for now. First, let's say parameters are given. Let's say train data parameter x equals 0 0.5 and y equals 0 0.8. Let's say weights and biases given these data, these values are the initial values. For the first layer, we multiply the input 0 0.5 by weight 0 0.4 and add bias 0 0.1. When we calculate this, we get 0 0.3. Since U1 is determined, we put this into the activation function. In other words, we calculate 1 divided by 1 plus e to the power of minus 0 0.3, and we get 0 0.574. For the second layer, we multiply 0 0.574 by weight 0.3 and add bias 0.2. Uh, then we get 0 0.3722. Since U2 is determined, we use this to calculate Z2. Z2 is 0 0.598. Since 0.592 is determined in the last output layer part, we multiply by the weight and add the bias. When we calculate this, we get the 0.596. Finally, when we put it into the activation function again, we get 0.645. The point is not to do specific calculation, but to see how parameters are determined. You can see that when U1 is determined, Z1 is determined. When U2 is determined, Z2 is determined. When U3 is determined, Y hat is determined. This is how calculations work inside feed-forward neural networks. Let's see how numbers are determined in the backpropagation method. The output is 0.645 for the previous result. So the value of the loss function is 0.645 as the predicted value. While the actual value was 0.8. So we square this difference uh, and multiply by 1/2. Then we get 0.012. So this corresponds to the square of the error. Let's calculate delta according to the previous calculation. Update for the output layer. Delta 3 is y hat minus 1 sigma prime u3. Here, sigma prime z is sigma z times 1 minus sigma z. Sigma prime u3, so u3 is here. Sigma prime 0.596 is about 0.229. So delta 3 is y hat is 0.645 minus y 0.8 times sigma prime u3, so 0.229. So delta 3 is about minus 0.036. Since delta 3 is determined, delta 2 is determined. The update formula for the second layer was like this. Delta 3 was calculated before. Double 3 is already determined as parameter from the beginning during forward propagation. So we know these two. So we need to calculate sigma prime use 2. When we calculate sigma prime the same way as before, sigma, so, since U2 is 0.3722, when we calculate using this, we get 0.241. Using this and arranging the previous numbers, delta 3 is minus 0.306, double 3 is 0.5, sigma prime u2 is 0.241. So when we multiply these, we find it's minus 0.004. Since we calculate delta for the second layer, next we can also calculate delta for the first layer. The calculation formula for delta is like this. So we just need to calculate sigma prime u1. Since u1 is where? U1 is No, 0.4, so it should be 4. When we calculated this, we find it's 0.245. So delta, so just misprint. So delta for the first layer is delta 2 is minus 0.004. Well, W2 is 0.3. Sigma prime U1 is about 0.245. So when we multiply these, we get minus 0.0003. This is how delta was determined. Since delta is determined, the values of partial derivatives for updating weights and biases are determined. The way to update weights and biases is to update W1, well, hmm, well, well. Means to update WL to the here. WL to the WL minus eta times DLDWL. We know that the partial derivative of L with respect to WL is delta L ZL minus 1. For bias, we know that we should update BL to BL minus eta DL since the partial derivative of L with respect to BL is delta L. We should calculate this. This was the update method by stochastic gradient descent. So we calculate like this. Since delta is known and z was already calculated during forward propagation, the numbers are already determined. So we just calculate it. Here, when we calculate with running rate 0.1 for W3, we should calculate the W3 minus eta delta 3 zeta 2. W3 is 0.5, eta is 0.1, delta 3 is minus 0.0636 here. Z2 is 0.592. So we get this calculation. This way we determine how B3, W2, B2, W1, B1 should be updated. The specific numbers are not important, but how the numbers are determined is, as we saw before, the error is determined, the difference between the predicted value and the actual value is determined, then delta 3 is determined, delta 2 is determined, and finally delta 1 is determined. Each delta was determined this way. You can see that the values are determined in reverse order with respect to layers, which is the opposite of the calculation in the forward propagation method we saw before. Using that delta, we finally understood how to update weights and biases. This is a specific calculation method of the back propagation method. Since we understand this far, we can now generalize it and we can calculate for any case. When we think about forward propagation of layer neural networks, let's still make the dimension of each layer 1 for now. Then the calculation of else layer uh, is to take the previous output 0L minus 1, multiply it by WL and add bias BL to get UL. We put this into activation function f, and what comes out becomes the output ZL of the else layer. Here, let's use the mean squared error as loss function. Data for the output layer becomes like this. Data for hidden layers has exactly the same mechanism as the three-layer case we did before, so it becomes this kind of update formula. Whew. This is data, and since data is determined in reverse order from the output layer, we use delta to update the value of each weight and bias. Here. Finally, let's make it a more general expression. Let's say the capital L layers and the dimension of each layer from N0 to NL. Uh, and we can similar calculations. Uh, well, so delta Li for each layer is calculated like this. It's simple with subscripts added. Here, so UL is ZL minus 1 multiplied by weight plus bias BL. Delta for the output layer when we use mean squared error as the loss function becomes like this. Delta for hidden layers need this kind of addition because of the influence of becoming a matrix. So to summarize, updating weights and bias using backpropagation. The method goes like this. First, delta for the output layer when we make the activation function or oh yes. First, delta for the output later oh okay, it's okay. So for first, when we make the activation function of the output layer, the identity function here. So just a minute. Okay, so here. So when we make the activation function of the output layer as the identity function becomes this kind of calculation. Delta for hidden layers. To calculate delta else layer, we use delta for the L plus ones layer and do this kind of calculation. By repeating this, delta is determined one by one from the output layer. Using this delta, we should update weights and bias like this. Hmm. So far, we have talked about what the calculation method seems to be like, but let's think about the meaning a little. What is delta? Delta for the output layer is simple. It represents the error between the correct value and predicted value of this training data. In stochastic gradient descent, we correct weights and biases to cancel out this error. Actually, this delta measures how much the output layer node contribute to the error. Delta for hidden layers also has similar meaning. What this means is, let's change the total input of hidden layer nodes. For example, let's say the total input use UI, UIL of the ith node of the else layer changes by delta U. Then how much the loss function change is when we think about Terra expansion, so L U I L plus delta U I minus is similar to times delta U. Oh, we need, well, oh, this is should be I. Okay, so by a level, so how much the loss function moved is delta use my so so this value how much is the loss function moved is delta L times so capital delta U, yeah. In other words, if delta small delta is almost close to zero, even if we adjust the total input of this node, the loss function will hardly change much. On the other hand, if the absolute value small delta is large, just a small change in this capital delta uh, you will cause the value of the loss function to change greatly. So if the absolute value of this small data is large, it means the inference is large. We can say that to approach the optimal value that minimizes the error function, we are adjusting parameters to give changes in the opposite direction to the change in the node's total input. By the way, the reason we do this backpropagation method is because our motivation was to calculate partial derivative with respect to weights and biases. There is a famous method called numerical differentiation for finding partial derivatives of functions. Numerical differentiation is that the derivative of g, for example, the derivative of g was defined like this. The limit of g of x plus epsilon minus g of x divided by epsilon as epsilon approaches 0 was g prime x of x. So if we take a sufficiently small number as epsilon, we can approximate g prime x. And this is the motivation behind numerical differentiation. So, when we want to approximate the value of derivative L with respect to Wi, we first calculate the value of L when we make it Wi plus epsilon, subtract the loss function when it stays as Wi, and divide by epsilon, then we can approximate the partial derivative. We could use this method to calculate partial derivatives. Hmm. The reason the propagation method is used more is the numerical differentiation is very convenient when the function is already specifically known. But in this case, various parameters influence each other not. So when we calculate this using numerical differentiation, we need to calculate the value of the loss function when we make it wi plus epsilon. For that, we need to perform for the forward propagation calculation. So we think the value of the loss function when w1 to wd are determined is already known, but we need to calculate again using uh, forward propagation how much the loss function becomes when we add epsilon to wi. So for each direction component of each W, when there are W1 to WD, we need to calculate the case where we add epsilon to each one. So the computational cost becomes large. Especially since the number of parameters is very large in neural networks. The computational cost becomes particularly large. On the other hand, the propagation method first, all unit outputs are determined in one forward propagation. Uh, all deltas are determined in one backward propagation. So computational cost doesn't depend on the number of parameters. When calculating using numerical differentiation, we need to calculate how the loss function changes when only one parameter changes for each parameter. We also need to calculate the case where it doesn't change, so this much computational cost is necessary. On the other hand, the backpropagation method simply calculates forward propagation and then calculates backward propagation. So the computational cost of the backpropagation method is only this much. So for neural networks with quite a large number of parameters, the backpropagation method is more efficient. Hmm. So far, we have used mean squared error as okay. Oh, no, no, no. So far, we have introduced the specific calculation method of the propagation back propagation method. But let's also briefly touch on its history. Backpropagation was published by Lamerhart and others in 1986 because the calculation method became efficient as we mentioned before. It caused the second boom of neural networks. This name backpropagation was also named by Lamerhart and others. But actually, such methods were known before this name was given. In 1960, it was taken up in the field of optimal control theory, and in 1967, Professor Amari formulated stochastic gradient descent for multi-layer neural networks. Actually, so before Ramera had proposed it, there were actually contributions from Japanese people too. Not only that, but after that too, although the name backpropagation wasn't attached, it was independently discovered by many researchers. However, there was a background that this knowledge wasn't widely shared. It was through Lamerhart and others that it came to be properly shared enough to cause the second boom, but it's worth knowing that the Japanese people also contributed, so please remember this. So far, we have used mean squared error as the loss function, but the binary classification problems, we use negative log likelihood. When dealing with binary classification problems, we use a sigmoid function as the activation function for the output layer, and that log likelihood loss is calculated like this. To calculate delta, we need to take a partial derivative, but since taking the partial derivative directly with respect to z is troublesome, let's first calculate the partial derivative with respect to y hat. When we take the partial derivative of this L with respect to y hat, it becomes like this one. Since y hat is sigma of z, the derivative of y hat with respect to z becomes sigma prime z. Since sigma prime z is sigma z times 1 minus sigma z, uh, so delta sigma prime z is y hat times 1 minus y hat. So delta calculated it becomes y hat minus y. So the delta for the output layer in the end becomes y hat minus y even in the class of log likelihood. So what happens in the case of multi-class classification problems? For multi-class classification problems, we use the softmax function as the output activation function. We use the negative log likelihood as the loss. To calculate delta, let's first consider the partial derivative with respect to y hat I. Taking the partial derivative of L with respect to y hat uh, is simply the partial derivative of log. Uh, so it becomes minus yi divided by y hat I. The derivative of softmax function becomes like this. Here, delta subscript ij is something that becomes 1 when I and j match, but becomes 0 they don't match. When we calculate, it becomes like this. So in the end, for binary classification problems and multi-class classification problems that we introduced in this class, In all cases, the delta for the output layer becomes y hat minus y. Hmm. This is what we get when we determine parameters using the propagation method for actual data. This is three-layer neural network with a hidden layer of 100 dimensions. And when we apply the sigmoid function as the activation function, we can see that it predicts red for red and blue for blue data like this. As you can see from this, the data is not linearly separable. So we can confirm that these neural networks can be applied even to the data that is not linearly separable. Now let's move on to talking about code. Now let's look at the structure of the actual code. First, let's prepare the library as usual. We prepare the sigmoid function and also prepare its derivative. We also prepare a function to calculate the loss function on negative likelihood and prepare the derivative of the loss function too. Simply, it's minus y hat minus y, but we can calculate it like this. However, here we divide by the number of data points. First, the initial function is to initialize weights and biases. Well, we need to decide weight and biases. By running this function, we get output that combines weights and biases. We just decide them randomly. We decide weights and biases using random numbers. Next, we prepare a function that performs forward propagation of the neural network using those weights and biases. The content is simple. For input x, we multiply by weight and add bias. Then when we output it into the activation function, which is a sigmoid function here, we call the value obtained from the sigmoid function z1, multiply it by weight and add bias. We put it into the sigmoid function, we multiply the by weights again and bias and put into the sigmoid function. We just repeat this process. This is the implementation part of forward propagation. Next, we also prepare the backward propagation. Here we know the input values and output values. Oh, oh. We know the input value and output value, and we put in how we calculate during forward propagation and what calculation result we got. Finally, we specify the learning rate. We are doing the calculation part for delta for the output layer that we did before. We calculate delta du1, du2, du3 correspond to that. And then we calculate the W3, which is partial derivative with respect to W3, and dB3, which is a partial derivative with respect to B3. After calculating this du3, which is delta 3, using du3, which correspond to delta 3, we calculate du2, which correspond to delta 2. Using this, we calculate the partial derivative with respect to O. Here. Using this, we calculate the partial derivative with respect to W2. Oh. And the partial derivative with respect to B2. Finally, we calculate du1, which correspond to delta 1, and using this, we calculate the partial derivative with respect to W1 and the partial derivative with respect to B1. Once we know these, we know how to update weights and biases. So we updated them according to the stochastic gradient descent method. By doing this, we get the updated results. So so the flow of the how to determine neural network parameter is first here. First, we decide weight and biases. Terrain part. We should see this part. Here. Yes, here. Okay, so first we decide weights and biases. For input data, we determine value through forward propagation. The value of loss function can actually be calculated with separate calculation, but here we calculate the loss function to see how much the value changes. Using the internal parameter obtained from forward propagation calculation, we update weights and biases by putting them into the back propagation function. Then we repeat this calculation. When predict what the actual value will be with the model, we can simply uh, calculate the value by doing forward propagation calculation. So this is the prediction part. Okay, so when we actually applying it, uh, we first preparing data, decide the parameters inside the neural network and use the previous function to determine the internal parameter to internal parameters of the neural network. Neural networks take a little bit of time. Oh, I forgot. Neural networks takes a little bit of time. This kind of data is given, and the result predicted for it are shown here. So when actually predicting where do you think 10 will be classified, specifically inside this, we run the predict function like this, since we calculate for a binary classification problem, we get probability. The probability of 1 is 0.119, which means we can confirm that the level is estimated to be 0. That's all. Oh, now please work on the in-class report.